So one of the topics that we'll discuss next is this idea of energy in electromagnetic waves. And when we talk about energy density, it's really, when we think of density, we think of volume. So it's the amount of energy in a volume. And for capacitors and inductors, we derived forms, and we had U, and that's equal to U of the electric field plus the energy in the magnetic field. And that was 1/2 epsilon naught electric field squared plus 1/2 magnetic field squared divided by mu naught. And these are from sections 24-4 and 30-3, if you want to review those. Now, since we usually consider energy as being split between both the electric field and the magnetic field, then we can make the formula that the energy is also equal to epsilon naught times the electric field squared, and that could be equal to the magnetic field squared divided by mu naught. And if we put in values from these equations and simplify, we can come up with also the square root of epsilon naught over mu naught times the electric field times the magnetic field. And all of these are equivalent. Also, we can put the magnetic field in terms of the electric field and the speed of electromagnetic waves, and this is equal to the E field divided by 1 over mu naught times epsilon naught, the square root of that, and simplifying, that's E times the square root of mu naught times epsilon naught. So we have all these different relationships, but we can look at what's called Poynting's vector to use these relationships in a useful way. So Poynting's vector is similar to intensity. It's defined as the amount of energy per time per area. Or it's the amount of power per area. We represent Poynting's vector by the variable s, and so we can write this as 1 over area times the energy change in time. And we can change the derivative of the energy to be some constant energy times a changing volume. And now I can put in my relationships from above. I'm going to use epsilon naught times E squared And for my volume, I'm going to use the area times the speed of electromagnetic waves times my differential time, and that all gets divided by differential time, and my A's will cancel out, my differential times will cancel out, and that just leaves me with epsilon naught times C times the electric field squared. Now we can use this relationship to come up with some others. So we can have the speed of electromagnetic waves times the magnetic field squared divided by mu naught. And we would have the electric field times the magnetic field divided by mu naught. And Poynting's vector is in the direction of motion, so in this case along the x-axis. So we can define a Poynting's vector, S vector, equal to 1 over mu naught times the cross product of the electric field cross magnetic field. Remember that a cross product means that the result is perpendicular to both the E and the B field, and the only direction we can have that happen is along the x-axis based on the way we have our orientation in the drawing. Now if we want to have an interest in average Poynting's vector, we just put S bar, and that's going to be equal to 1/2 epsilon naught times C times the electric field squared, and that's also equal to 1/2 C over mu naught times the magnetic field squared. And also, again, we have E naught, or I'm sorry, I'm just doing E's at this point. Electric field times magnetic field divided by 2 mu naught, and this is for sinusoidal. Waves. This is what our average value would be for sinusoidal waves. So now with Poynting's vector, we can come up with expressions that will take us back to some mechanical analogs, and we'll be able to relate this to something in a actual forces that we can play around with.